Joint work with Santosh and Kevin. So before jump into the actual robust estimation problem, here's a quick recap of what is a classical estimation problem. Suppose we are given independent points from a distribution, and we want to estimate its mean and variance or covariance. What we would do is what you would think is just sample mean and sample covariance, and you can show that this works pretty well for a wide class of distributions. So a running example would be a normal distribution, but which I'll be referring to again and again. But what this talk will apply for a much more general class of distributions. So if this is the model and if this is how the data is, then the problem is essentially easy. What John Tukey asked in 1962, he's one of the people behind fast Fourier transforms, was what happens if there are errors in the model? What if the data is not exactly coming from your model, but there's some deviations? And it has since become a field, an entire field in statistics called robust statistics. It's a lot of work in this, and the question can be the central question asked in this can be summarized as how do estimators, different estimators, do in a neighborhood of the model? So usually, like say sample mean, you can show does very well when the data is exactly coming from the model. But what if when the data comes from, around not exactly from the model, but in a neighborhood of the model?
So when you say the model, you mean the distribution?
Yeah.
And then you sample. There's some sort of adversary between you and the distribution. You sample, but you get something that might not be right.
Right. Yeah. So I'll make this very concrete in a couple of slides. Okay. Let's just take as a warm-up, let's take 1D Gaussian. Okay. So and we have 1D normal distribution. And what do we actually mean by a neighborhood of this? Well, not quite this. I'll make it more concrete. So we'll assume that there is an adversary which adds eta fraction of noise. There are many ways of formalizing what we mean by a neighborhood of the distribution. This is one of them. It's a natural one and initially proposed by Huber. And what this means is, say we have m samples. 1 minus eta fraction of those are sampled independently from the distribution. And remaining eta fraction are chosen by an adversary arbitrarily. In fact, the adversary can look at those 1 minus eta fraction and then pick these points. Slightly stronger than what Huber defined initially. And this would be the model we'll consider for this talk. Okay. If you have any questions, feel free.
At this point, the combination of the two is no longer a distribution formally?
Yeah, it's not. So what Huber defined initially was adversary picks a distribution to begin with, and with 1 minus eta fraction, you get points from the two distribution. But with eta fraction of the points are sampled from an adversarial distribution.
A simpler model would be, but maybe it's trivial, is that the combination of your original sample and your noise forms a new distribution, and how does its mean and variance compare to the one you want, right?
Right, yeah.
And that's probably well studied, I guess, right?
Yes, that's one that's usually studied in robust statistics. This is slightly stronger. Yeah.
So the adversary can see the sample you get.
Yeah. Adversary can see the sample and then pick the theta fraction of the points. Okay, so then the question is we want to estimate the mean and covariance of the distribution. And the way we measure the performance is, so we want to compute a mu hat and a sigma hat so as to minimize the two norm of mu hat minus mu. Mu is the true mean and sigma is the true covariance, and we want to minimize the Frobenius norm of sigma hat minus sigma. Okay, so and as applications, you can think of, so if you have a class of distributions parameterized by mean and covariance, then you can think of it as finding the best fit distribution, but with when the data is not actually coming from the distribution. And like many other problems in machine learning, say ICA, independent component analysis, or SVD, relies on first, many of the approaches rely on first computing the covariance matrix. Now, if you can do it in the presence of adversarial noise, you can hope to do, and you can do those problems too under the same model. As an example, like if you first compute sigma hat and compute the top k, the best k rank approximation for sigma hat, then it works, it's a good rank k approximation to true sigma too. Like you can give this bound where you can show that even in the presence of adversarial noise, this is close to the best rank k approximation. Okay. We would need some assumptions on the distribution. The one we will need is this, which I'll refer to as having bounded fourth moments, which means that in any direction, the fourth moment of the distribution should be at most C4 times the variance in that direction squared. Many like sub-Gaussian, sub-exponential, or any distribution with finite fourth moment all satisfy this. And also like I'll treat C4 as a constant for the talk, though in the paper all the bounds are made explicit in terms of the dependence on C4 is made explicit.
What's sub-Gaussian?
Sub-Gaussian is something whose tail is less than or equal to Gaussian tail. Like,
you would need this assumption even if there was no noise, right?
Even if you don't have, probably you can do with weaker assumption. If you just say you want to compute the mean.
Yeah, but for covariance.
Oh, for covariance, just probably 2 plus epsilon moment is sufficient rather than like fourth moment. And yeah.
So how about Cauchy?
Cauchy, no, doesn't fall under this because it doesn't even have second moment.
Okay, that's that one.
Yeah. But then you can still ask for mean, but you can't do robust mean from our algorithm.
Sure.
Yeah. Okay, so first I'll state the results, then walk through the algorithm. Okay, this automatically goes through the next slide. Okay. Anyway, so I'll denote the maximum variance of the distribution by sigma square, the small sigma square. And let the distribution have mean mu and covariance sigma. Then the main result is that we can compute a mu hat such that it is at most square root eta times sigma times square root log n away from the true mean. Okay, so
Do I lose anything by assuming this is just in one dimension?
This
As opposed to a distribution in higher dimensions? Is it crucial that?
so this n is the dimension.
Oh, I see, okay, good.
But yeah, the lower bound. So lower bound has no dimensional dependence.
Okay.
So Ideally, you would want something which doesn't have n in it. Yeah, you can show a lower bound. You can't do better than eta power 3/4 times sigma. So there is a square root versus 3/4, which is suboptimal. There's a gap between lower bound and upper bound. And also the dimensional dependence, square root log n.
Where's the sample size?
Sample size is here. It's close to linear, like n log square n. Right, yeah. So we need like order n sample, order O tilde n sample to give this guarantee. Now if the covariance is spherical, yeah?
So, but what's the dependence of the bound on M?
Bound on M?
M. So in the sense that as M goes to infinity, does the bound go to 0?
Yeah, yeah. Oh, sorry. It doesn't go to 0. This is the, if there is eta fraction noise, you can't do better than this, regardless of how many samples you have, because these are chosen by an adversary. Right, yeah. Now, if the covariance is spherical, sigma square I, which means variance in every direction is same, then we can get optimal dependence on eta. So eta power 3/4 lower bound and upper bound are same. Still, there is a square root log n factor which can probably be removed. Okay, so that's the case for distribution with bounded fourth moment. If you are just looking at Gaussians, then there was a simultaneous paper which could give this guarantee. Eta sigma square root log 1 over eta. So there is no dimensional dependence, and as well as dependence on eta is optimal. Depends on how you look at this factor, but close to optimal guarantee in the case when the distribution, underlying distribution is Gaussian. Okay, any questions at this point? Then I'll move on to covariance estimation. The algorithm remains essentially the same. And suppose we have m points sampled. Okay, by d eta I mean like eta chosen by adversary and 1 minus eta chosen independently from the distribution. Then consider this second order objects x minus. So if you have m points, pair them up arbitrarily and construct these second order objects. And now if you look at the expectation of this of yx, then it will be the covariance matrix. Now you can think of these objects as, instead of looking at this as matrices, you can think of this as n square cross 1 vectors, whose expectation is the covariance matrix. So you can apply the mean estimation algorithm to estimate the covariance matrix. And what we can show is that with O tilde n square samples, we can get a sigma hat, an estimator for the covariance matrix, which is at most square root eta log n times 2 norm of the covariance matrix away from the true covariance matrix. And this is like a standard trick done to avoid computing the mean. So now once you pair them up and take the difference, the mean is 0 of the distribution. So you can avoid the step of having to compute the mean first and then applying the algorithm. But other than this part, the algorithm remains the same. So I'll just focus on mean estimation part.
So is this with high probability?
Oh, yeah, this is with high probability.
So what's the probability?
This is with 1 minus 1 over poly n. Yeah?
What's the lower bound
So here the lower bound, I'm not sure it should be, so I'm not 100% sure, but my guess is it's eta, the dependence on eta should be still eta power 3/4. In 1D case, if you just look at 1D, then it is eta power 3/4 sigma. In higher D, that still works for a spherical covariance thing. I don't know if there is a stronger lower bound. Yeah?
So for the Gaussian case, is the sample complexity different or is it the same?
Sample complexity will be, in the thing they solved, it is similar, n polylog n. Yeah, I don't think there is an order n kind of sample complexity. Oh, and for covariance estimation, we need same condition but with bounded eighth moments, because we are actually applying the algorithm to the second order objects. So instead of bounded fourth, we need eighth, and also some independence between the coordinates. 8-wise independence is sufficient. This is to relate covariance matrix of the second order objects to the covariance matrix of the original distribution. Okay. So let me start with just simple one-dimensional case, and then we'll move on to higher dimensional case and see why it is non-trivial, why most of the existing algorithms don't work well. Okay, so just consider 1D Gaussian, okay, and we want to estimate the mean under this model. Eta fraction is bad. If you think of sample mean, even if one point is chosen by an adversary, sample mean does very badly, because adversary can place the point at infinity and the sample mean will be way off from the true mean. But a moment's thought you'll probably come up with sorry. Let me. So sample median works well. Sample median has an error of order eta sigma. So in 1D Gaussian case, 1D Gaussian case, you can just compute the sample median and you're done, and it matches the best upper bound. So yeah.
So what's the algorithm again? So what are you going to do?
So we are given the sample, m samples, and we just look at the median and output that as our guess.
Oh, I see. Okay.
And this is for the mean.
This is for mean estimation. Okay. For variance estimation, there are multiple ways, but one that is widely used is this median of the absolute deviation from the median. So first you compute the median and look at the deviations of every point and look at their median. And that up to a scaling factor will have an optimal dependence. So you can show that it's not me doing that. I can't, it's just skipping to different slides. I'm probably not doing something right here. Okay, so you can, if you do this, look at median of medians, you'll get sigma hat minus sigma to be like order eta sigma, which is optimal. Questions?
What is C0?
C0 is an explicit constant you can compute. Like it's for normal distribution, there is a specific constant. For bounded fourth moment, median doesn't work. Why? This example is, so it's just a Bernoulli distribution with probability half on minus sigma and with probability half at sigma. Even without noise, median doesn't work, because if you say have even number of points, either you'll get, if you look at the median, either it will be sigma or minus sigma. It's way off. Do you have a guess as to what? How can we fix this? Just 1D case. All we know is it has bounded fourth moments.
Does the Gaussian have bounded fourth moment?
Yeah, it has bounded fourth moment, but it has much nicer properties too.
Right.
Yeah.
It avoids this problem.
Yeah, right.
So remind me, so let's see, so in the continuous case, I understand you take derivatives and stuff, right? Yeah, so what do you, what's the moment here mean for the discrete case?
Oh, it's just the, you just compute this expectation, just like say expectation of x power 4 for various values. So in this case, the fourth moment, the mean is 0. So x minus mu will be, in absolute value, is always sigma. So fourth moment will be sigma power 4. Second moment is sigma squared. So it's here C4 is 1 actually. C4 1 works. So thing that a solution that works is look at every interval. Look at an interval which contains 1 minus eta fraction of the points and minimize the length of the interval. Okay? And compute the sample mean of the points lying within this interval. And you can show that this has the optimal dependence. The error will be like eta power 3/4 times sigma. And same, you can do the same to estimate the variance too. Look at the smallest interval that contains 1 minus eta fraction of the points. Compute the variance or the standard deviation of the points within this, and this will have the optimal dependence. Okay, so let's go back to the normal distribution, but higher dimensions.
Well, could you give, so what happens in that case when you do that?
So 1 minus eta fraction of the points. If you want to capture this, you'll you'll consider mean, sample mean of all the points, essentially all the points. Because if the adversary places noise here, close to here, but all eta fraction of the points here, to capture 1 minus eta fraction of the points, say 1 minus eta over 2, just to, you'll consider the all the points essentially, like the interval will be whole, this entire thing, and you look at the sample mean of that.
Okay.
And since the adversary has only eta fraction freedom, the error will be like at most eta sigma in this case, when you look at the sample mean.
This is the clean data also,
This, what I've shown here is clean data, but now you can add eta fraction of noise to this. This method is for noisy data.
So the median has the benefit of not requiring you to know eta. Is there a way to do this without knowing eta?
No, I do, not that I know of. We need for. Is it possible? Not sure of that too. Yeah. Let's go back to normal distribution but higher dimensions. Here things to consider would be like median. There's no unique definition of median in higher dimensions. Here are a couple, coordinate-wise median. You can take median in each of the bases, and that's one case. Or there's geometric median, which is the minimizer of sum of L2 norms. But you can show that both these, in the worst case, the error will be eta sigma square root n. So the dimensional dependence is bad. This has a square root in the dimension. And pretty much this was almost the state of art for robust statistics in terms of computationally feasible methods. Just to recall, ideally you don't have, like the lower bound has no square root n and no dimensional dependence. So we don't think there is n here. And an example that is bad for geometric median as well as coordinate-wise median is here. Like say this is all the Gaussian points, and your adversary places eta fraction of the points in like a diagonal position. Now you can show that both geometric median and the coordinate-wise median will have an error of like, which depends like square root n. There is a thing called two-key median, which is in robust statistics literature, and the advantage is that it has optimal error guarantees. You can show that it's like eta sigma, but the unfortunate thing is it's NP hard to compute. There are approximations. I don't know if Gary remembers, but he has a paper from a long time back which to compute 1 over d factor approximation with Shongo and others. But yeah, so there are a lot of
Hard is actually, if I give you one and I ask you, is it a median? But the question of finding one may not be hard. There's this little point between I'd like to know, is this a center point or whatever? And the other question is, find me one.
Yeah. But if you can find one, you can answer the other question too approximately.
So by a two-key median, you mean one that has maximum two-key depth?
Yeah.
Okay.
Because if you can find one, then you can say answer yes to in a small neighborhood.
You may want to define what two-key depth is, but okay.
Yeah. Right. So and so the past 10-15 years, there's very little activity in like robust statistics literature because all the estimators are very computationally infeasible and works at most to 6 dimensions or so. And the other ones, like the medians, have bad, like things that work well in practice have square root dimensional dependence. There was nothing better known until now. Recently, there have been a series of papers. Okay, so let me give some kind of a motivation for our algorithm. So in higher dimension, consider this to be the case. So here the red points are chosen by the adversary, blue are the Gaussian points. And suppose, in addition, someone told us what is the direction of this shift. This is the Gaussian mean. This is the mean of Gaussian points and the noisy points. And I call this mean shift vector. Delta shift is the mean shift vector. Suppose we knew the direction of this. Then this problem is easy. Why? It's one-dimensional, yes. So we can reduce it to one-dimensional by projecting all the points onto the n-1 dimensional space orthogonal to the mean shift direction. We know that there is no mean shift in this space, so we can just compute the sample mean, and that would work. And then we are only left with this direction. We can project everything onto one dimension and output the median. And we know that it does well. Error is eta sigma. So it's sufficient to know this direction. Right? So natural next guess would be, would the top principal component of the covariance matrix work? Would that be along this direction? But a moment's thought would say you, like if you place 2 points symmetrically at, say, infinity, you can make that direction to be the top principal component of the covariance matrix without having any mean shift in that direction, because you placed it symmetrically about the mean. So top principal component doesn't work. Okay, so but our algorithm in some sense works towards finding this mean shift direction. Okay, so now let me be more specific. I'll describe the algorithm in detail now. It involves two steps. We iterate over them. First is a weak outlier removal step. If there are points that are like at infinity or like far from the rest of the distribution, we can throw it away. Okay. And the second step is we compute. Then we have done the weak outlier removal step. Then compute the covariance matrix. Compute the top n over 2 principal components and bottom n over 2 principal components. Project all the points onto the top n over 2 principal components and recurse. This is essentially the algorithm, and I'll go over it in more detail in the next few slides. And in the bottom n over 2 principal components, we can show that there is the mean shift vector is very small, so you can just compute the mean by sample mean. Okay, so here is the algorithm. There are 5 bullet points. If dimension is 1, I'll just assume the distribution is Gaussian, and assume the median works in dimension 1. Otherwise, if it is bounded fourth moment, you can do this 1 minus theta, smallest interval that contains 1 minus theta fraction of the points, and that works. So if dimension is 1, you just output the median and you're done. Otherwise, you look at the coordinate-wise median. Now, it's not a good estimator. Error is like eta times sigma times square root n. There is a square root n dependence, but it's not terrible. It's some kind of an estimate. And look at a ball of radius c sigma square root n around the coordinate-wise median, and throw away all the points outside it. Okay, so we have this input, and we construct a ball of radius c sigma square root n around the coordinate-wise median, and throw away all these points. Once we have done this procedure, we ensure that every point is within a distance of c sigma order sigma square root n from each other, and also you preserve all the Gaussian points, because all the Gaussian points are concentrated around sigma square root n from the mean, and we can pick this c large enough so that you preserve all the Gaussian points and throw away only the noise points. Okay, so throw away all the noise points and then compute the covariance matrix of the remaining points and the top n over 2 principal components and the bottom n over 2 principal components. And then we project onto the top n over 2 principal components and recurse the entire procedure. In the bottom n over 2 principal components, we just compute the sample mean. We project these points and compute the sample mean.
So this is basically generalizing the projection to one dimension, to doing it.
Yeah,
piece
yeah.
by piece, having the dimension.
Right, having the dimension. But if we just did it one dimension at a time, we'll again have square root n dependence. But since we are having the dimension each time, and we can show that in the lower half, sample mean is very good, we can get a much better dependence on the dimension. In the whole n over 2 dimensional lower half space, we incur only eta sigma error. Okay. Once more. So input is Gaussian plus noise. We construct a ball around the coordinate-wise median and throw away all the points. And then the main point is that when we look at the mean shift vector after doing this weak outlier removal step, its projection onto the bottom n over 2 space is very small. So we can just output the sample mean. Any questions on the algorithm? Otherwise, I'll go and show why this works. Okay. So let me denote this input point, set of input points by S, and the covariance matrix by sigma S. The mean of the Gaussian is mu, and mean of Gaussian plus noise is mu S. Okay. We can write the covariance matrix in terms of the covariance matrix of the Gaussian and covariance matrix of the noise part. So here, this is there's 1 minus eta fraction of Gaussian points. I'm ignoring the sample complexity, etc. I'll assume the sample covariance, the covariance matrix of the Gaussian points is exactly equal to sigma square I, just for simplicity here. So this is the Gaussian part, and this is the covariance matrix of the noise, and then there is a component because of the mean shift vector. Okay. So what outlier removal step ensures is it gives us a way to control how much the noise perturbs the n over 2th eigenvalue. Why? Because once we have done this outlier removal step, we know that every point is at most within a distance of sigma square root, order sigma square root n away from each other. Right? Now, if you look at the covariance matrix of just the noise points, okay, and look at the trace of those, it's equal to the expected squared distance from the mean. And since each point is at most sigma square root n away, the trace will be order sigma square n. So therefore, the trace of eta times sigma n, the covariance matrix of the noise, is at most eta sigma square n. So this is what weak outlier removal step gives us. Now, just to say, I gave an example why top principal component doesn't work, because you can place 2 points symmetrically at infinity, but outlier removal step throws away these kind of points. But you can still show that top principal component doesn't work. Even with outlier removal step, if you look at the top principal component, that doesn't work. Okay, so we have this trace bound. Now let's look at the sample covariance matrix, and we'll write it as the Gaussian part plus whatever is remaining. I'll call it as matrix A. We have bounded the trace of this, eta sigma n. We can bound the trace of this as well. Delta shift is, just to recall, it's the mean of the Gaussian minus mean of the sample. Now that will be eta times mean of the Gaussian minus mean of the noise. And since every point is within sigma square root n away, the length of delta vector is like sigma square root n. So the trace will be eta square sigma square n. So the trace of this whole matrix, trace of A, is going to, we can bound by eta sigma square n. Now we'll apply Weyls inequality. It says that n over 2th eigenvalue or any eigenvalue is the top eigenvalue of this matrix, the Gaussian part, plus n over 2th eigenvalue of A. Now since we have a bound on the trace of A, the n over 2th eigenvalue of A can't be bigger than eta sigma square. So just to put it, putting things together, n over 2th eigenvalue of sigma s can be at most 1 plus order eta sigma square. Now that's very close to the actual, if we didn't have any noise, then the n over 2th eigenvalue will be like sigma square I. We are only order eta sigma square away. Any questions? Okay, so now that we have bounded the n over 2th eigenvalue of sigma s, that also gives a bound on all the eigenvalues below it. It can be at most 1 plus order eta sigma square. Now that lets us control the length of the projection of the mean shift vector. So the projection onto the bottom n over 2 space of the mean shift vector is this red one, and we can show that its length is small. Why? So let's look at the projected vector. So look at delta shift and project it onto the bottom n over 2 space. And since we know a bound on the n over 2th eigenvalue, the Rayleigh quotient of W, this quadratic form is at most 1 plus order eta sigma square, just because it lies in the bottom n over 2 space, eigenspace. Now to get an upper bound, again recall what sigma s is, and observe that since this is a covariance matrix, this is a positive semi-definite matrix. Now if we hit this now with W transpose W and ignore the term coming from here, we get the following inequality. So 1 minus eta sigma square, that's coming from this part, and I've ignored this, it's a positive quantity. And when I hit W transpose W to this, since it's a projection of delta vector onto the bottom n over 2 space, I get the projection square. Okay, so I have a lower bound and an upper bound, and if I combine, and notice that these two terms cancel, the leading term cancels. So then the next leading term is just order, so there is an eta sigma square here and an order eta sigma square here. So putting it together, we get that the length, the mean shift vector, the length will be like eta square sigma square, length squared. So that this was key, that the leading term cancelled. If the this matrix, if this matrix, the Gaussian matrix, is not spherical, then in the lower bound we won't have this. The lower bound will be lambda min, and this leading term wouldn't cancel, and instead of eta square we'll have an eta. So it will be a worse dependence, and that's why the difference of spherical covariance versus a general covariance matrix exists in the bounds that I showed at the beginning of the talk. Okay, so putting this all together, what we have shown is that the bottom n over 2 eigenspace, the error, if you just compute the sample mean in the bottom NO2 eigenspace, the squared error is like eta square sigma square. And in the top NO2 eigenspace, we just recurse. So we have to recurse log n steps. And in each step, we incur an error of eta square sigma square. So putting it all together, we'll have eta square sigma square log n. That's what gives us the square root eta sigma square root log n error. And we didn't use much about Gaussian distribution. So other than this handling the 1D case in a different way, and also the weak outlier removal step is slightly different, the main central part of the algorithm remains the same. Okay, so questions? This is essentially the entire code, except for one small subroutine that's missing. And you might wonder how it does in practice. So here is a plot for an example. So here goes all the way up to, it's for mean estimation, all the way up to dimension 2000. Takes a few seconds. And this is the geometric median. You can see it growing with the dimension. And the red one is the one output by the algorithm. It stays very flat and also close to the, if you just threw away all the noise points and computed the sample mean, that's what blue is. And it stays pretty close to it and also flat. There's no like, it doesn't grow with the dimension. And we also gave this as a
But there's a log n dimension term in the.
Yes, that comes from the analysis. We're not sure if that is required. Square root log n.
Square root of log n.
Yeah.
That's pretty slow growing.
That's pretty slow growing, and we are not even sure if it's just an artifact of the analysis. We tried hard to construct examples that would be sharp for this algorithm, and we don't know of any. And in fact, we gave this as an assignment problem to one of the class where people could just come up with any distribution and plot things. And all the plots looked pretty much like flat.
But this doesn't include the runtime or anything, so this chart, this is just the accuracy.
This is just the accuracy, yeah. Yeah. The running time, so it requires an SVD. So if you just do a pure theoretical analysis, it's not that great, but there are very fast implementations of SVD. So I did this in MATLAB, and it takes 3-4 seconds for probably like 10 seconds for dimension 2 for all the 3 cases.
But that would have the log factor in the dimension.
No, it will.
Wouldn't it? Because you're recursing.
Log n SVDs.
Recursing having dimension having.
It will have.
Are you solving both parts of that? No, wait. Oh, you're taking all the points and you're projecting them down to over 2 dimensions.
Yeah, right.
So you do have a log factor in the dimension, right?
In the running time?
Yeah.
Running time will have like log n times SVD, but SVD of varying dimensions. But the main thing is analysis has this square root log n, which we don't see in the, yeah. So in summary, so what we have is an algorithm for robust estimation of mean and covariance. And it works for a wide class of distributions. Just we need bounded fourth moment. And sample complexity for mean estimation is linear up to log n factors. And for covariance estimation, it is like n square, but it's a Frobenius norm guarantee. But that is At least for mean estimation, it is practical. For covariance estimation, it is not practical because you construct, if you have, for example, I'm not sure if I can do more than 100 dimensions because you construct this n square cross n square matrices. So if you want to do a covariance estimation for an n-dimensional problem, you construct n square cross n square matrices and do SVDs on them. So some open questions would be, can we give an algorithm that matches the lower bound for general distributions? For Gaussians, it's almost solved. In fact, it is solved now. There is optimal now. But for general, it's just fourth moment bound, there is a gap. And it's not, there's a gap in eta dependence between eta power 3/4 and square root eta, and also there is the square root log n factor, which probably can be avoided. And if instead of Frobenius norm estimation of the covariance matrix, what if we just wanted in operator norm? Seems like a more natural thing. If you just cared about mean estimation, you can just deal with operator norm estimation of the covariance matrix, and then you can reduce it to a spherical case. But we don't know of any algorithm that works well. And in fact, even linear number of samples are sufficient for just operator norm estimation. And time complexity, practically also it is very bad. All the algorithms at the moment construct these n square cross n square matrices, which is a bad idea. And you can ask this problem for various kind of learning problems. Gaussian mixture model. What if small fraction of the points are chosen by an adversary? There are papers now, recent, like a few months back, some learning Bayesian networks. And yeah, so almost any learning problem, you can put it in this setting and ask whether you can do it robustly. Yeah, that's pretty much it. Thank you.
At some point, I thought you would bring in leverage scores.
I was in my earlier versions of the talk before the Gaussian case got solved.
So at this point, maybe I missed, you didn't use leverage scores?
No, we didn't use
And
leverage.
it's not clear how to, or? Because I guess classically in statistics, they've been used to eliminate outliers, right?
Yeah. So that kind of elimination you can show you can give an example where you eliminate only the good points and preserve all the noisy points. So it's pretty. There are examples where we can place noise points. Adversary can place noise points very carefully, so that even if you remove eta fraction of the points, it will be all good points, and you'll still have all noise points remaining.
I mean, the other thing you talked about is, I guess, Tukey point, right?
Yeah.
So, I mean, there's all these other heuristics that at least experimentally we use, like this Cascaded Radar.
Okay.
So, you would just look at small samples and compute a center point for those, and then you would cascade that.
What do you mean by?
I mean, we could talk about all
Okay.
point, but there's another thing called Teuberberg points. These are points that are provably center points.
How good, like?
We can talk about
Okay,
that, but
okay.
we haven't looked at any of that. But
I
it's
see.
curious whether any of these other things that work,
I see.
at least empirically work well or not.
Right.
We
Yeah.
don't have the guarantees.
Okay. Yeah. Right, okay. Yeah. I think just Tukey median, even for general, like these are distributional. What we do is essentially find Tukey median, but under distributional assumptions, like average case complexity. But if you want an 1 plus epsilon approximation, I think that's also hard for Tukey median.
For Gaussian, there's still square root of log n gap between lower bound and upper bound?
Not anymore. So there was like instead of square root log n, there was square root log 1 over eta. But in the spherical case, even that has been removed. The paper is not out yet. So it's like just eta sigma in the spherical case. So that's Gaussian case, that's just matches the upper and lower bound, but you should know the covariance matrix for that.
Thank you. So is this classic algorithm of Floyd for best for computing the median?
Sorry?
Floyd and